Hi there. Welcome to another amazing day with Chem Coach Powers learning some chemistry for physical science. Today we're going to be talking about some pretty cool things. We're going to be talking about different types of reactions and what those reactions are. Once you learn their basic structure, then it helps you to predict what kind of reactions are going to take place if you have similar situations. And so learning these reactions are going to help you to make predictions on reactions you've never seen before, being able to predict the results of those. Okay, so as we get going here today, our objectives. This is 7.3, to be able to identify which of 5 general types of reactions a given chemical reaction belongs to. We could talk about another one called oxidation reduction. We're not going to talk about that, but we'll talk about 5 other types. So let's talk about our reactions. We've got synthesis reactions, and of course, synthesis means to put together, right? And so synthesis reactions are examples where you have 2 separate types of elements or compounds coming together to make one new structure that has a compilation of their new properties in it, okay? And so reaction with 2 or more substances combined to form a new compound. This is the general form. A plus B gives you AB. Now notice we've kind of color-coded those because we want to see the example below and how this kind of corresponds. I've kept all of the symbols like the plus signs, the arrows, and then the coefficients and the subscripts. I've kept those white. But I just want you to see that A is yellow with sodium, right? B is kind of like this tan color, and that's chlorine. When you bring them together, it's yellow sodium with the tan chlorine. Okay, so what we're seeing here is that general structure, the A plus B gives you AB. Those aren't actual elements that we're talking about. We're just talking about an example of the types of elements that are coming together to form new products. So a good example for a synthesis reaction is when you have sodium and chlorine coming together to form sodium chloride, all right? So this would be an example of a formation of salt, table salt. Okay, so this is a synthesis reaction, and then this synthesis reaction is one in which you've got hydrogen and oxygen coming together to form water. Okay, this is probably one of my favorites because it deals with an explosion. Okay, so if you want to watch this video, you can just type in supersonic detonation of hydrogen and oxygen gas. You're going to be able to see that in YouTube. Okay, if you watch this separately, you can get some cool stuff out of there. But I think that it's kind of fun because you get to see in this reaction how when you get a mixture of hydrogen and oxygen gas, that you actually get a much bigger explosion because you have oxygen as something that's helping to help that reaction take place. But it's so cool that fire is making water, okay? Hydrogen exploding is making water, and fire makes water. It's one of my favorite things about fire. Okay, so this is another type of synthesis reaction, and this synthesis reaction is one in which you see photosynthesis. Notice here I've got photosynthesis, right? Now this reaction doesn't quite fit the model that I just gave you, A plus B gives you AB, because it also has this extra little O2 that's also part of it. Now that's okay, it's not your typical synthesis reaction, but scientists do consider this a synthesis reaction. There's a few different types of synthesis reactions. One's called dehydration synthesis, and there's different types, but the idea here is that you're taking smaller pieces and putting them together into a bigger piece, okay? So I just wanted you to know that there are other synthesis reactions, even though it's not classic in this case. All right, what other types of reactions do we have? We have a decomposition reaction. Okay, so synthesis and now decomposition. Where synthesis is putting things together, decomposition is pulling things apart. And so reaction in which a single compound breaks down to form 2 or more simpler substances. And so here we see the A-B structure again, together on the left side of the reaction where it's on the reactants, and now as a product, it's an A plus B. Examples here, we can see that exactly the opposite. It's 2H2O gives you H2, 2H2 plus O2. And so here we've got the opposite of the reaction we just saw where hydrogen was exploding and making water. Now we've got the water coming apart and making hydrogen and oxygen gas. Now this is a really cool reaction as well because this is a reaction that we call an electrolysis reaction. And you can see that when you take a battery, and you can even just do this with a 9-volt battery, you put that 9-volt battery into a glass of salt water, and you're going to see this actually taking place. Now, look over here. It's kind of cool because when you look at this tube here and you compare it to this tube here, notice how the distance is quite a bit different between the two levels, right? This tube has got more gas in it. Basically, it seems about twice as much, doesn't it, as this tube? Well, that really makes a lot of sense when you think about the reaction. Remember that that reaction was H2O gives you H2 plus O2, but don't forget that there were there were coefficients in front. If I take two H2O molecules, I'm going to make two H2 molecules and one O2 molecule. Can you guess which one is the hydrogen gas and which one is the oxygen gas? The one that has twice as much of the volume of gas is going to be the hydrogen gas, right? So this is our hydrogen gas, and this is our oxygen gas. Isn't that kind of neat? You can actually see as it breaks apart that the ratio of the moles, remember we talked about mole ratios, the ratio of the moles is visible with the actual volume of gases. Isn't it fascinating and fun? All right, so let's go on and talk about another form. Now, this other form of reaction is called a combustion reaction. And a combustion reaction is going to be typically a hydrocarbon, which means it has hydrogen and carbon in it. And reacting with an oxygen is going to create carbon dioxide and water. Okay, these are our products typically of a combustion reaction. Now, different books and the internet, if you go looking for combustion reactions on the internet, you're going to see some slightly different definitions of it. Okay, but this is the definition that we like to use. And up here it says organic compound, and so in this case we're talking about a hydrocarbon. Now CXHY is the way I like to symbolize a hydrocarbon. C, a certain number of C's, and then a certain number of H's. Okay, the X and the Y being the variables of certain numbers. You take that and you're going to get carbon dioxide and water. Notice that heat is released. So if I were to add heat to this reaction, I could basically just put plus heat. These are exothermic reactions, okay? And the reason they're exothermic is because these molecules are going to a lower potential energy state. They're actually more stable as water and carbon dioxide than they were as the combined hydrocarbon, right? The gasoline, for instance, or sugar if it's in your body and how you're eating sugar and it's producing carbon dioxide and water inside your body. Okay, so remember that combustion reactions do depend upon the amount of oxygen. And if you have a different amount of oxygen available, then you're not necessarily going to get all of carbon dioxide as your product. You're actually going to end up getting carbon monoxide as your product sometimes. If you don't have enough oxygen, you get carbon monoxide. Okay, so that's a combustion reaction. And again, a typical combustion reaction is anything involving fire of a hydrocarbon. So when you burn wood, okay, in this case, we have methane. This is the natural gas that you have in the lab when you're burning in the Bunsen burner. You take the methane, you combine it with oxygen, you get carbon dioxide and water. Again, notice that our law of conservation of mass is holding true. I've got 8 oxygens over here, and I've got 8 oxygens over here. I've got 2 carbons. I've got the 8 hydrogens total and the 8 hydrogens total. So combustion reaction, the meaning is that you are burning an organic compound, in this case a hydrocarbon, and forming the carbon dioxide and water. And again, the internet will talk, for instance, sometimes you might find a source that would talk about the hydrogen explosion that we said is synthesis. They might say that's combustion because it's producing heat. Some books will define combustion reaction as something that produces heat, in this case, heat or light, but not in our case. Okay, so let's look at our next one. This is called a single displacement reaction or a single replacement reaction. Those two are synonymous with each other, and basically it's a swapping. I like to think about this as like a dancing relationship, and you've got a couple that goes to a dance, and there's a lone person over here, and the lone person sees, ooh, I'd like to dance with him, taps on the shoulder and starts replacing them. Okay, so now you've got a new partner that you're dancing with instead of the partner that you were with before. But it starts with a single entity and then a coupled entity, right? And then one of them, it gets replaced, okay? And so in this case, it's going to be the more reactive element that is going to take the place of the less reactive one. Okay, so if you see, in this case, we've got A, X together. They come to the party together, to the dance together, and then here comes B. If B is more reactive, then B will replace A. However, if B is not more reactive, then A is just going to stay, or X is going to stay with A. And so the idea here is, again, I like to think about the dance, maybe one of them is cuter, and so they replace it, versus, oh, no, you're not cute, I'm going to stay with my, partner I have here. Okay. All alkali metals and some other metals undergo similar single displacement reactions with water. So alkali metals are going to react with water. Why? Because the alkali metals like sodium and lithium, cesium, all those are all going to be more reactive than hydrogen, right? So if I have hydrogen and I've got sodium, okay, then sodium is going to replace the hydrogen. If this is H2O, sodium will replace the hydrogen and it'll become NaO with that another little H left over still. And so this is a reaction in which if you put sodium in water, then you're going to get sodium hydroxide as one of your products. That's kind of like a plus sign. If I did sodium plus water, I'm going to get the reaction of sodium hydroxide. Okay, so then you can see this other reaction. Again, we've kind of color-coded them here. In this case, we've got copper chloride and aluminum. And so the question is aluminum more reactive than copper? Well, the way that we would know that is by looking at something called an activity series. You're not going to have to worry about that this year. In the future, in chemistry, you're going to learn about the activity series and using that to determine if a reaction takes place here. Okay, but in this case, yeah, it takes place. Aluminum must be more reactive if this reaction takes place. It displaces or replaces copper. Copper is left alone. Aluminum is dancing the night away with chlorine. Woohoo! Okay, so let's go and look at this reaction. We can see that aluminum foil, when you put it into a solution of copper to chloride, actually is getting replaced. And this aluminum foil basically turns into this brownish substance, and it's a bunch of copper that is now kind of sticking to the leftover parts of the aluminum foil. And the aluminum has now entered into solution. It's a really cool reaction. It's actually pretty awesome. Some of it, there's one where you can do this with copper sulfate as well, copper 2 sulfate. It's even faster and more violent. It's pretty exciting. All right, so then we have our next reaction type, which is called the double displacement. And the double displacement reaction is basically two people, these two couples come to the dance party, and they're like, oh, you're cute, oh, you're cuter. And they basically, swap with each other, right? So they find better partners. The reason this happens is in order to, get to a more stable energy state for the most part, right? And so for instance, when I start with this A and B, A and Y are going to end up together. All right, so you can see over here that the A and the Y end up together. It's forming typically a solid precipitate. These reactions, these double displacement reactions, tend to happen in order to form things like water or other types of new compounds that'll come out of solution, solid precipitates that come out of solution. But they're finding a more stable energy state overall, but they are ending up as an insoluble form of this new product, okay? So typically that new, one of these products is going to be an insoluble form. In this case, this one would be the insoluble one. It would have a solid after it. Potassium nitrate is still going to be in solution, and so this would be aqueous, and this would be aqueous. They're just in water. And then when you finish, the sodium, potassium nitrate is still aqueous, but the lead 2-chromate is actually going to end up being a solid precipitate. And so again, this is a double displacement reaction. The partners are swapping, and you end up with something really cool. Now, this is the reaction we were just looking at. And you take these two clear liquids, when you pour them together, it forms this yellow substance. Now, that yellow substance is lead 2-chromate, which we were talking about there. And that actually is something that is a heavy metal waste. I don't typically do this reaction in class even, because it's a heavy metal waste that you have to have taken away. You can't put it down the drain or down the trash. It's considered dangerous, and so we don't typically do it, but it's a really cool reaction to look at, and that literally is what happens. You pour those two liquids together, and you form this yellow cloud, which if you let it dry out, turns into a solid powder. So can you identify these general forms? I want you to take a second. You're going to pause and practice, and I want you to see if you can figure out what these different ones are. Okay, so pause it. And you're back. Now let's see how you did. This top one, I hope you figured out, was a double displacement reaction. This one has that formation for a combustion reaction, right? This one is synthesis. This one is a single replacement and or single displacement. And you might have also, sometimes I'll call these double replacements over there. And then this last one is a decomposition reaction. Okay, so hopefully you're able to do that. Now comes the next test, and a little bit harder test. Can we actually identify a reaction in real life, a real reaction, and then figure out what it is by looking at the patterns? Okay, so let's look at this first one. Hydrochloric acid plus sodium hydroxide gives me sodium chloride plus H2O. Now I want you to see something here. H2O is a lot like saying HOH. And that might help you see a little bit of relationship there. Can you figure out what kind of reaction it is? Okay, I'm going to go ahead and click through on these next ones. See if you can identify all 4 of these types of reactions, and pause it and practice, and then we'll come back with the answer. Ready? Pause. And you're back. And so if you look at it, the OH here is still an OH over there, right? And so basically we took the H and we replaced it with an Na, and then on the Cl, okay, that was now with the Na, whereas before it was with the H. Okay, and then our OH here has now become part of the OH here, and so our H, this is a double displacement reaction. Are you seeing it? Double displacement or double replacement reaction because they're just swapping partners, okay? If we were looking at it, this would be A. Let's say this is AB, and then let's say this is called CD. Well, now A is over here with our hydrogen, and then B is here, right, chlorine. C was our sodium, and then our D was hydroxide. So look, we have new partners. Before we had AB together, now we have AD together. You see it? We have new partners. Before we had CD together, now we have CB together. So we've come up with some new partnerships there. On this next one, look, we only have one product. If you ever have just one product, that should be an indicator to you that you have a synthesis reaction, okay? So that's going to be synthesis. On this case, we have an Na that was with Br, and now Cl is with Na. Oh, so Cl must have replaced Br, but there's only one partner that gets to swap, so that's a single replacement reaction. Okay, so then we have our Na and our H2O, and here we have Na. And again, remember, H2O is the same thing as saying HOH, right? So now Na is with the OH. Oh, so let's do the little letters here. A, and then B and C, and then this is still A. Oh, but my OH is now here, and my B is now here. So my AC is together, whereas before my BC was together. My A swapped out and replaced my B. So this is another example of a single replacement reaction. Did you get them right? I hope so. I think you're figuring this stuff out. I imagine you are because you're super smart. Let's go and let's see about these others. Now, you notice it's telling us to balance first and then identify the type of the reaction. For a test, you would want to balance it and then identify. Right now, we're just going through the identification part. But it's not hard to balance these, right? So why don't you do a little pause and practice? Go ahead and balance these. See how you're doing on your balancing. Double check yourself, and then we'll see if you can also identify the type. Ready? Pause and practice. And we're back. All right, so I've got 2 OHs here, which means I'm going to have to put a 2 in front of that, right? Because it said I had 2 oxygens. So on this side, I had 2 oxygens and now 2 hydrogens, 1 barium. On this side, I now have 3 oxygens. Oh, boy, that's okay, right? 4 hydrogens, that's okay. If I've got 4 hydrogens on this side, I can put a 2 in front of that to get 4 hydrogens on that side, and also that gives me 4 oxygens. Well, if I put a 2 in front of my barium, now I'm good, okay? Wait a second. Wait, so that was balanced before? No, I must have screwed something up. All right, so let's just do it the old-fashioned way. Ba equals 1 initially, Ba equals 1 initially. OH, I'm not going to keep those together. I'm going to separate them out. So O equals 2, H equals 2. Over here, I had O equals 2, H equals 2. We were balanced in the first place. I'm such a little dunce sometimes. I'm so silly. Okay, so when I saw that they were all 2s, I thought, oh, I either screwed something up or remember, you reduce them down to their lowest whole number ratio, and so you wouldn't want to have each of those. Now, I was just silly of me to not see that OH didn't balance on the other side. Okay, so what kind of reaction is it? Well, it separates out. Starts on one, if you ever have one reactant, and then you have multiple products, and you're probably figuring out, oh, this has got to be a decomposition reaction, right? All right. Fe plus O2. Okay, I've got 2 irons on this side, but only 1 on this side. So if I put a 2 there, that makes the irons balanced. But now I've got 3 here and 2 there. Let's find our least common multiple, which would probably be a 6, right? And so that makes that 6. I've got to do a 2 over there to make that 6, which means we've got to swap that out and make that a 4. Okay, so now it's balanced. What kind of reaction? Well, it goes from 2 reactants to 1 product. And so this must be a synthesis reaction, right? All right, now I've got a hydrocarbon. Hopefully you're recognizing that hydrocarbon. Let's see if we can balance this. I've got 2 carbons on this side, so let me put 2 carbons on that side. And now I've got 6 hydrogens. If I put a 3 here, I'll have 6 hydrogens. But now I've got 3 oxygens, and I've got 4 oxygens. That means I'm at a total of 7 oxygens. I'm going to tell you a little trick. If I do that and I put a 3.5 there, all of a sudden it balances my oxygens, because 3.5 times 2 will actually equal 7. You can't leave it that way, but it's a little trick to kind of do a temporary balancing. And so now I have a 3.5. I have to get rid of my half. I've got to double this. I've got to double that. I've got to double that, and I've got to double that. So now my final balanced chemical reaction is 2, 7, 4, 6. And of course, this is a unique structure. It has a hydrocarbon plus oxygen, giving me a product of carbon dioxide and water, so that's a combustion reaction. All right, on this one, I've got 2 aluminums over here, so I'll throw a 2 there. And I've got 3 sulfates, so let me throw a 3 there. That gives me 6 potassiums. Let me throw a 6 there to get my potassiums good. And now my hydroxides are 6, 6, aluminum, boom, I'm done. Okay, so that's like a 1 right there, right? And so now this has got a lot of things in there, and yes, if you look at it carefully, they're swapping partners. So this is a double replacement or double displacement reaction, okay? Did you get them? I know it probably took you a little while to balance that and to come up with those solutions, but if you practiced it, you will know where your mistakes are. And if you just wait and you watch me go through and do this stuff, you are not learning. You've got to practice it yourself and then see where you made mistakes. Practice each one. Don't be like, yeah, I couldn't figure out the second one, so I stopped and I let you show me the rest. Practice each one. Maybe you'll get the third or the fourth one if you didn't get the second one. Make sure you hit your head against a brick wall, because when you hit your head against that brick wall, that's where you start doing your learning, okay? And then, of course, you see my answers that might help you a little bit. So let's see if we can now, meet our objectives. Given a chemical reaction, can you identify which of the 5 general types of reactions they belong to? I think so. I think you've done a great job today. I hope you have an awesome day, and I hope you were kind to others. Chemistry is awesome, and so are you. God bless you. Have a good day.